Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tear. And as I do every Saturday, usually, I missed yesterday because I was out with my cousin who I hadn't seen in over 15 years. We went hiking, we had a really good time. But I usually do this feature on Saturday, biographies of famous mathematicians, but I got delayed one day. So I'm doing it today, and today is one of the biggest. Carl Friedrich Gauss. A lot of people think he was the greatest mathematician of all time. I think it's a toss-up between him and Euler. I'm not sure who was greater, but I'd say it was one of them two. A lot of people say Euler was more for quantity and Gauss for quality. I mean, Euler did published, I think, 30% of all the mathematical publications that were published by anybody during his lifetime. I featured him a few weeks ago, and he came up with some pretty great results. But Gauss, I think Gauss more for quality. He didn't publish quite as much as Euler, but just about all the results he did come up with were really kind of revolutionary and pioneering work. So really, really amazing mathematician. Anyway, yeah, here's my page on him on the Math Lovers book. He was born in 1777. He was German, and he lived till 1855. And he's been called, I think, the Prince of Mathematics, and just an amazing amount of work. I'm going to profile some of the greatest results he came up with. The first really amazing thing he did, this was around age 10. I don't think we even know exactly how old he was when he did this. I've heard different figures. I've heard as low as age 7, but apparently what happened, this is a very famous story. He had a math teacher who asked the class, I don't know if they asked the whole class or just him, but he wanted them to add all the numbers from 1 to 100. And of course, I don't think the math teacher knew any faster way to do this than just to add them all one at a time, which takes a really long time. But Gauss, as a child, discovered this amazing trick, and what he figured out was that you could add these numbers very quickly just by pairing them in the right way. I mean, if you um, for instance, pair 1 with 100, 2 with 99, 3 with 98, so on, all the way up to 50 and 51. I guess they're doing this twice. But uh, I think you can see there's 50 pairs, and each of those pairs adds up to 101. So the sum is 5050. If you know the trick, you can do it very, very fast, which he did. I think he did it in about a minute, and the teacher couldn't believe it. And the teacher checked it by hand, which I think took most of the length of the class to do. And he was amazed that Gauss got the right answer at age 10. I don't know if he ever told the teacher the trick he used or not. But anyway, and you can use this trick. I mean, you can generalize this trick to any value of n, and you come up with a very important formula. These numbers are called triangular numbers, by the way. Sums of all the numbers from 1 to n. That's known as the nth triangular number. People usually write as t sub n. And the reason it's called a triangular number is because it's the number of objects if you arrange them in a triangular array, side length n. This is just the number of objects in the array. And the general formula is n times n plus 1 over 2. Probably some of you have seen this formula. It's a very useful formula. But I don't think this formula was really well known before Gauss. It was discovered before Gauss, but I don't think it was used that much. And Gauss discovered a derivation of it. And that was one of the first things he did. And then still when he was, I guess he was a teenager when he came up with this. I've heard different figures on his age. Either the first time I heard this, I heard he was only 16 years old. I think it was actually 19. But he came up with a really amazing geometric construction. I mean, the ancient Greeks were really interested in geometric constructions. They wanted to know what kind of geometric figures you could construct with just a compass and a straight edge. And I think they knew how to construct a regular pentagon, which is already a very difficult construction. I never even learned that in high school myself. Uh, but Gauss discovered an even harder construction. I mean, it turns out you can't construct an arbitrary regular polygon. It has to have a special number of sides. And if it has a prime number of sides, I'm not going to explain why this is true, but it is true. The only prime number of sides, the only constructible polygons with a prime number of sides are polygons with 3, 5, 17, 257 or 665,537 slides. Those are all special primes known as Fermat primes. I think I talked about those when I was talking about Pierre de Fermat. They're really 2 to the 2 to the n plus 1, where n goes from 0 to 4. So the intermediate case, the third case of those is 17. I mean, obviously, a regular triangle is constructible, equilateral triangle. Greeks figured out how to do a regular pentagon. Gauss discovered the third case at age 19, regular heptadecagon, or usually people just say 17gon. Very, very difficult construction. I think you can see this. These are the steps he used to construct this thing. I don't know how he figured this out, but he did at age 19. And not only that, not only did he figure out the geometric construction, he also came up with a mathematical formula. He came up with an algebraic construction, which gives you a closed form expression for the cosine of 2 pi over 17. I don't know if you guys can see it, but it's this formula in blue at the bottom left. I've actually done this derivation myself. I've never constructed a regular pentagon, I mean heptadecagon, but I do know how to derive this form. It's a very, very difficult derivation. I wrote out a derivation a few years ago, 7 pages. You have to use a lot of algebraic number theory. But Gauss did this at age 19. He was the first person to do this. Pretty amazing, I think. And another thing he did was he discovered a type of complex number known as Gaussian integers, which have a lot of very useful properties. You can even talk about Gaussian primes. I did do a video on this. So a Gaussian integer is just a complex number of the form a plus bi, where a and b are both integers. That in and of itself isn't all that special. But what's really neat about Gaussian integers is they form what's called an integral domain, which just like the ordinary integers. You could talk about Gaussian primes. So you could generalize the notion of prime numbers to Gaussian integers, and Gauss did exactly this. And you get unique factorization for Gaussian integers in the same ways you do for ordinary integers. So Gauss was the first person to study these numbers known as Gaussian integers in his honor. And this is a picture of a German stamp. This was commemorating I guess it was 1977. This was commemorating his 200th birthday, what it would have been his 200th birthday. Or maybe it was the 200th anniversary of Gaussian integers. It was probably that. But I just want to say one thing while I'm on this slide. I have seen several stamps commemorating mathematicians. This is one for Gauss, who was German. And I think that in India they made a stamp honoring Ramanujan, who was another really amazing mathematician. But I don't think there's ever been any American stamps honoring a mathematician. And, I'd love to see one of these days, but I don't think I will because Americans don't seem to care about math that much, which I think is very unfortunate. Um, but anyway, enough of my preaching. Um, what else did he do? He did a lot of work with number theory. He came up with a concept known as modular arithmetic. He kind of pioneered modular arithmetic. This is a pretty simple idea. You just do arithmetic. It's like you're dealing with remainders. So you do arithmetic modulo m, where m is some positive integer. We actually do this when we tell time. I mean, hours on a clock are the hours are mod 12 because the hours on a standard clock only go up to 12. It would be arithmetic modulo 12 if the number on top was 0 instead of 12. But that's the idea. You can add two numbers and take them, find the remainder mod m, or you can multiply two numbers, find the remainder to mod m, and they turn out to obey the same properties as ordinary numbers. Associativity, commutativity, distributivity. You can even make a group out of them. Ring. Anyway, so Gauss kind of pioneered this, and he came up with another really important concept. I'm not an expert on this, but I think you guys are probably familiar with arithmetic and geometric means. I mean, arithmetic mean is just the ordinary mean you usually study. You take the sum. You take the sum and divide by two if you're just doing two things. And then for the geometric mean, you take the square root of the product of the two numbers. But what Gauss came up with was sort of an intermediate mean. This is now known as the arithmetic geometric mean. You kind of take the mean of the arithmetic mean and the geometric mean, and it's an iterative process. You have to do this infinitely many times, but it converges very quickly. And it is a very well-defined mathematical concept. And it actually has a lot of important applications. I think the main application Gauss used the arithmetic geometric mean for was studying elliptic curves or elliptic functions. Might have not been elliptic curves. Maybe it was both. I don't know. It turns out the formula for the arc length of an ellipse, that's what's known as an elliptic function. And you could actually derive the formula for an arc length of an ellipse, was a very difficult calculation, but you do it using the arithmetic geometric mean. So I just thought I'd mention that. What else did you do? Gaussian curvature. So he was interested in topology as well. Topology and geometry of surfaces, and he kind of knew. I guess he knew about non-Euclidean geometry. Maybe he was one of the pioneers. I don't know, but he came up with this notion of the Gaussian curvature of a point on an arbitrary surface. And sometimes you see these three examples. They got the sphere on the right. Sphere has a positive Gaussian curvature everywhere. And the curvature of a sphere, every point on a sphere is just 1 over r squared, where r is its radius. It kind of tells you how much, how much is, I don't know how to explain this in a good way, but you can't flatten it into a plane. If you try to, I mean, if you peel an orange, maybe you guys have done this before. An orange is roughly spherical. If you peel an orange, you can't really flatten the orange peel onto the table without distorting it. But you can do that with a cylinder. Cylinder has zero Gaussian curvature, so you can unroll a cylinder onto a table, and it doesn't crumble. And then the sort of opposite case of a sphere is this hyperboloid. This has a negative Gaussian curvature. Um, and maybe I should say this another way. I mean, this is sort of non-Euclidean geometry we're talking about here. So, I think you guys all know that in regular geometry, Euclidean geometry, if you take a triangle and you add the angles of a triangle, they add up to 180 degrees. I'm sure you guys all learned that when you were learning geometry at some point. But if you did the same thing on a sphere, you would get a sum of angles that's greater than 180 degrees. And if you did it on a hyperboloid, you get a sum of angles that's less. And the amount which is less or greater is depends on the Gaussian curvature. You can write that difference in terms of the Gaussian curvature. That's why this is an important concept. And another thing he did, this is another thing in number theory, quadratic reciprocity. I don't know if I should explain this or not. It's a little bit complicated, but this basically has to do with when numbers are squares modulo a prime. So maybe I can give this easy example, like 2 is a square modulo 7, because 3 squared is 9, which is 2 mod 7. So we would say 2, we write this kind of thing, it looks like a fraction with parentheses around it. Um, we would say 2 with a, the 2/7 with parentheses around it. That's what's known as a Jacobi symbol, or that's equal to +1, because 2 is a square mod 7. 3 is not a square mod 7, turns out. Um, but what Gauss discovered, if P and Q are primes here, so it turns out that P is a square mod Q. If P is a square mod Q, then Q is also a square mod P whenever either P or Q is congruent to 1 modulo 4. That means that these two Jacobi symbols their product is equal to +1 in that case. The only case in which P is a square mod Q, but Q is not a square mod P, is when P and Q are both congruent to 3 modulo 4. And Gauss proved this. And he came up with a really nice geometric proof. There's actually hundreds of proofs of quadratic reciprocity, but Gauss came up with the first one. And he did come up with a really beautiful proof of this fact, which I'm not going to go over. But it's a very important result in algebraic number theory. But anyway, and then not just in math, those are kind of his great mathematical accomplishments. But he was also did a lot in physics, particular regarding electricity and magnetism. And for anybody who studied, electricity and magnetism, you probably know about Gauss's law. This is a very important law, and I'll just explain this. I actually did a math video recently where I solved a problem involving Gauss's law. So I'm just going to tell you what this law says. So imagine you have a bunch of charged particles. This is what they're showing here: Q1, Q1. I guess they have two Q1s and one Q2. But you can have any. They don't even have to be point charges. You can have any distribution of charge particles, and then if you put a closed surface around those particles, and it doesn't have to be a real surface, just an imaginary surface. And here it looks like they're showing a sphere. And then what you do is you calculate what's called the electric flux through the circuit. That's just the integral of all the electric field over the surface. I'm not even going to try to explain what that is, but it turns out there's a very easy way to calculate that electric flux. It's Gauss's law. And it turns out that the total electric flux through any closed surface is equal to the total amount of charge enclosed in that surface. That's capital Q enclosed, and then you divide by this constant. This is the permittivity of free space, epsilon naught. That's just a physical constant. So a pretty amazing formula, and it really allows you to do some calculations that would be much, more difficult without it. There's actually a law that's very similar for gravity, but nobody seems to use it. I don't know why. Because gravity and electricity and the electrostatic force are both inverse square forces. They I think you guys all know about Newton's law of universal gravity. F equals gm1 m2 over r squared. Coulomb's law for electrostatics looks almost exactly the same. It's just you have a different constant k, and then you have q1, q2. It depends on the charges, and then again the square of the distance. But anyway, equivalent formulation of Coulomb's law is Gauss's law. So very important law. And another important thing that Gauss did, I guess he collaborated with another famous physicist, this guy Weber, and he was, I think, an English physicist. But together they invented this device known as the Gauss-Weber magnetometer. And this was a very useful device. I don't know if people still use it, but it's used to measure the strength of the Earth's magnetic field, which was very important at that time. I remember we're talking about early 19th century years. So knowing the strength of the Earth's magnetic field and its direction was very important, especially for navigation. So that was another thing that Gauss did. Amazing accomplishments for Gauss, which I think he puts him either in first or second place of all the mathematicians who've ever lived, in my opinion, anyway. But anyway, that concludes. There was one more thing I forgot to mention. Also, I think most people who study, electricity and magnetism, at some point you probably learn Kirchhoff's laws. I don't know why they just say Kirchhoff's law. There's really two laws here. But there's the current law. I learned this as the junction rule. If you have a junction with an electric circuit and you have a bunch of currents going in and a bunch of currents going out, it just says that the total current, if you like, the sum of all the currents going in minus the sum of all the currents going out, that sum is equal to zero. And that's just a statement of conservation of electric charge. Basically, just saying the electric charge can't build up or be depleted at the junction. It has to be conserved. As much currents going in as going out. Kind of intuitively obvious. And then there's also Kirchhoff's voltage law, which says that if you measure the voltage drop of a bunch of components in a circuit, going around the whole circuit, that total voltage drop or voltage gain has to be zero. And that makes sense too. That's just a statement of conservation of energy, just saying that, the total potential energy going around the circuit has to be, it has to go back to what you started. So, uh, you know, but one thing I just learned today, I just learned this today. Kirchhoff did discover these laws, but it turned out he wasn't the only one who discovered them. Gauss did too. I'm not sure why it's not called the Gauss-Kirchhoff laws, because Gauss also discovered both of these laws. Anyway, I just thought I'd mention that. So, yeah, that concludes my feature on Carl Friedrich Gauss. Like I said, one of the greatest mathematicians of all time. So, thank you for watching. Long live math, and I'll see you guys next time. Bye.